the Unit 7 Building Block 4 notes packet. Part 3 is the last part. So we're going to finish up today, and then tomorrow we'll be doing some practice. And then quiz Friday. And then next week we will be reviewing and then testing. So yesterday, or the past 2 days really, in part 2, we focused on arithmetic sequences and series. That was when we were adding or subtracting a number continually to get to the next term in the sequence. Okay, that number was called the common difference. Okay, we subtracted consecutive terms to find it. In geometric sequences, there is what's called a common ratio between consecutive terms. Okay, a ratio is division. So instead of finding the difference, which was subtracting, we're going to divide consecutive terms to see if there is a common ratio. So you can see, take any term divided by the previous term. So the third term divided by the second, or it could be the 17th term divided by the 16th, or the 100th term divided by the 99th term. Okay, and if those all come out the same, that is R. That's your common ratio. Okay, so in arithmetic sequences, D was the common difference. In geometric, R is the common ratio. So we're going to practice example 1 here. We're going to just find R. So we want to divide any term. So I'm going to start with the last term by the previous term. Okay, or you could do 36 divided by 12. Okay, so we can do it twice since we have 3 terms. And when I do that, both of those come out to 3. They're the same. So that means that the ratio, they have it in common. It's a common ratio. So that is R. And what that means is to get from term to term in my sequence, I am multiplying by 3. So arithmetic sequences, you were adding a constant each time. Now you're multiplying by the same number each time. Okay. Does that make sense? All right. So part B is a little more complicated because you're dealing with fractions, but you're doing the same thing. So we're going to take negative 1/27 divided by the previous term, which is 1/9. And when we have fractions, we can flip and multiply, right? Dividing fractions is easy as pie. Flip the second and multiply. So instead of dividing by 1/9, we can multiply by 9/1, which when you multiply fractions, you just go straight across. So that is negative 9/27, which reduces to negative 1/3. And then we do the same thing and check that it's the same. 1/9 divided by its previous term, which is negative 1/3. And we'll flip and multiply. We're multiplying by negative 3/1, which going straight across, that's negative 3/9, which also reduces to negative 1/3. So they are the same. We do have a common ratio of negative 1/3. Now, when your common ratio is a fractional value like this, like 1/3, multiplying by a fraction, we just said multiplying and dividing, you can just do the reciprocal and do the opposite operation, right? So instead of multiplying by a fraction, a third, that's the same thing as doing what? We can think of it as multiplying by negative 1/3, or if I change it to dividing, what does the number change to? Instead of 1/3, it's negative 3. So if it's easier to think of it as dividing by a whole number, okay, than multiplying by a fraction, you can do that. Those mean the same thing. Just like when we had our common difference in arithmetic, if it was negative, we just thought of it as subtracting instead of thinking of it as adding a negative. We good? All right, so that's a common ratio if we have a common ratio, that's a geometric sequence. Okay, so we're multiplying to get from term to term instead of adding. So there are, just like there was for arithmetic, there are multiple types of formulas to write the equations. There is explicit, which in arithmetic, it was dn plus a sub n was dn plus c, or is that linear format, kind of like y equals mx plus b? It was dn plus c. For geometric sequences, these are not linear functions, okay? So it's not going to be similar to that, but we still do have our first term, a sub 1 still means first term, multiplied by the common ratio to the power of n minus 1, where n is the term number, okay? So this is definitely not linear, right? All right, so it's different than the arithmetic. Now, if you don't know the first term, the a sub 1, but you know some other term, we'll call it just a known term. We're going to call it a sub k. We could use a sub k instead of a sub 1. So you can see here, I just replaced that. But I also have to replace the 1 in the exponent with a k. Does that make sense? So if you know the first term, this is a sub 1 and this is a minus 1. But if it's some other, like if it's the 8th term, you would plug the term in there and then this would be an 8. Does that make sense? Okay, that's explicit formula. Now recursive, remember, recursive was when we use a sub n minus 1. And we know that that means previous term. We talked about this notation in part 1 and again in part 2. So this is the third part of the notes. We're talking about this meaning the previous term. So recursive formula is saying, it's like saying the rule. You just take the previous term times r. Okay, so if your ratio was 3, it's saying just take the term times 3 and take the new term times 3 times 3 times 3 times 3. It's just recognizing the pattern. So we're going to practice that in the next couple of examples. So in example 2, they want the first 5 terms. Of a geometric sequence whose first term of 3, so that's a sub 1 is 3, and whose common ratio is 2, so that's r. So that's pretty simple. You are taking the first term, 3, and you are continuing the pattern by multiplying by the ratio. This is your recursive formula we're using. We're just doing it in our head. We're saying you take the previous term times the ratio. So to get the second term, the previous term is 3 times 2. Now I take that term times 2. Does that make sense? So you can use recursive formula to fill in a sequence of numbers in your geometric sequence. Okay, as long as you know the first term and what that ratio is. Now sometimes, like in example 3, you're asked for a higher term number. Like this is asking for the 12th term. That's a sub 12. They do give you the first term still. And the ratio. There's not supposed to be an n there. So I could, in theory, go back and do what I did here and just start with 20 and multiply times 1.05 times 1.05 times 1.05 all the way until I get to the 12th term, right?
Yes.
That would take a while. So that's why we have formulas. To get a specific term number, in this case the 12th term, if you know the first term and the common ratio, this is the formula you can use. So we're going to plug in our first term. It's 20. Our ratio is 1.05. And the term number that I'm looking for, the n, is 12. So a sub 12 is 20 times 1.05 to the 12 minus 1 power. Those are the values that I plugged in. You do get a calculator. You don't have to do all this by hand, but that's 1.05 to the 11th power and then multiplied by 20. And that comes out to be 34.207. Does that process make sense? So it's very similar to what we were doing with arithmetic, where we have a formula, we identify the first term, the common ratio instead of the common difference now, and the term we're looking for, and we're just making sure we plug things into the right part of the formula. And again, I'm going to give you these formulas when we test. These will be on a formula chart. Okay, I won't have labeled what every little piece of it is, but the formulas will be there, but you need to know what to plug in where, okay? And when we quiz over it, it'll be open notes. You'll get to use all of these notes. All right, in example 4, we want the 15th term. So again, that is n. The term that we want to find is 15. And then they give us the first 3 terms of the sequence. So I can identify a couple of things from that. What is the first term? 5. Okay, so I have the first term is 5. I just want to color code this. Okay, I did blue. Okay, so the first term is 5. And then what else do I need for my formula? I need the ratio. Good. I've got the a sub 1 and I've got the n. So to figure out your ratio, how are we going from term to term here? Okay, some of you can just see it. You're like, oh, that's being multiplied by 3. Fantastic. If you don't see it right away, or if it's decimals or fractions, something that you're not as quick to see it with, remember, you just divide consecutive terms. So you could do 45 divided by 15. Or you could do 15 divided by 5. Those both come out the same to 3. That's our R. Okay, so a sub 1 is going to get plugged in there. We said n will go here as 15. And then that R we just found to be 3. So I'm going to input all those values. 5 times 3, and that ends up being the 15th power, or excuse me, the 14th power, since it's 15 minus 1. So this number is going to get really big pretty fast, right? It's 3, multiplying by 3 over and over and over again, 14 times, right? This comes out to be 23,914,845. So that grew really quickly. I could have just continued the pattern and said times 3, times 3, times 3. Until I got to the 15th term. But again, that would have taken longer, and that would have been a lot more typing in the calculator too. All right, 5 is a little more complicated because we are not given consecutive terms. They give us the 4th term is 125. So that's a sub 4 is 125. And they give us the 10th term. So a sub 10 is 125 over 64. They don't tell me R, the ratio, and these are not next to each other in the sequence, so I can't simply divide them, can I? So unfortunately, we're going to have to do, before we can answer this question about what's the 14th term, I have to know what R is. Again, another typo, I don't know why that N is there. So we have to find the ratio first. So step one, we're going to use that same formula, except instead of A sub 1, I'm going to do A sub k. Because we said if you don't know the first term, but you know some other term, we'll just use A sub k to represent that instead of A sub 1. And then it will be N minus k instead of N minus 1. Everybody good with that? Now I have to solve for R. R is unknown. That means I have to plug in for everything else. So I know 2 terms. So I'm going to be able to plug in those 2 terms here for these 2 A values. But which one should be N and which one should be K? I would always make the larger term, like the term further in the sequence, N, because you're doing N minus K. And you don't want to end up with a negative exponent that you have to deal with, right? That's going to make it more complicated. So should N be the 4 or the 10? I want to do 4 minus 10 or 10 minus 4? Yeah, so I want N to be the 10th term. Okay, so I want to do A sub 10 will go here. And then I will make the 4th term, actually I'll do a different color here. My K, so K is 4. So then A sub K is 125. Does this make sense? What I'm about to write is just extra. You don't have to change it to this, but for it to maybe make a little more sense, you could show that we're replacing N with 10 and we're replacing K with 4. So if you want to show that, that's what's getting plugged in here. That if that makes it make more sense to you, great. So A sub 10 is 125 over 64. A sub 4 is 125. R is unknown. That's the whole point of this, is to solve for R. N is 10 and K is 4. Everybody okay with what I plugged in where? Now this is slightly more complicated because I have to work backward to solve for R. So what's the first thing I need to do to solve for R? How can I get rid of this coefficient of 125? Yeah, so I'm going to divide out the 125. What you do to one side, you do to the other. But here we've got a fraction and a fraction again, right? And we said you can flip and multiply. So instead of dividing by 125, we're going to multiply by 1 over 125. And seeing it that way, I can clearly see what happens to the 125s. Yeah, those reduce. Common factor in the numerator and denominator. So that's just 1 over 64. So I've got 1 over 64. And this is going to be the 6th power, right? 10 minus 4. So I've got 1 over 64 is R to the 6th. How do I get rid of the 6th power? Okay, if it is square, I square root. If it is the 6th, I take the 6th root. So the opposite of raising something to a power is taking the radical, okay? But it's not always called the square root. Square root implies that it's a 2 here, which is the understood index. You need your index of your radical to match whatever your exponent is so that they actually cancel each other out. So we are taking the 6th root of both sides. This is not something you have to know. You're able to do this in the calculator. So we do want to review how to plug that in the calculator. Okay, so to get the 6th root, or any root other than a square root, you go to the math menu here. And it is the 5th option down. See, it has X as the index. So that allows you to put any number as the index that you want. So I want the 6th root, and then I have to arrow in under the radical and type in 1/64. Let me grab the phone. Hang on. There, Kyle. Yes. Yes. Okay. So we got 1/2, 0.5 or 1/2. So that is our R value. Yeah. Now, that was not what the final question is asking. They didn't say what's R. They said find the 14th term. But now that we know R, we can do the second part of this problem, which is using that same formula to find the 14th term. So here now, N is 14. Okay, I'm looking for A sub 14. And I now know R is 1/2, so that's going to go here. And then I can use the same purple. A sub 4 was 125. I plugged a 125 in here. And then the K was the 4. So I can use those same values. The only thing now is I don't know the A sub 14. I got 125 times 1/2 to the 14 minus 4. So that is 1/2 to the 10th power times 125. So the 14th term is 125 over 1,024. That's what that comes out to. So that kind of mirrors the question in part 2, where we had to do the same thing with arithmetic. We were given non-sequential terms, and the first part of the problem, we had to first work the equation backwards to find D, and then we used D to answer the question. Okay, so similar setup there. It's just geometric this time, so it's a different equation. Any questions so far? All right, now we talked about arithmetic sequences being linear models. Looking at these equations, where is N in these? It's in the exponent. What type of function is that when your variable's in the exponent? Same root word. The variable's in the exponent. It is a exponential function. Okay, so that's what this is saying right here. Okay, it's saying just as arithmetic sequences were linear, okay, geometric sequences are modeled by a specific type of function. And because the variable is in the exponent, that is exponential functions. Now it does say with a limited domain of natural numbers. What that means is that it's a discrete graph, meaning we don't connect the points. Okay, it's that curve that it grows exponentially really fast, right? So it's this shape, but it's discrete. We're not connecting the points. Okay, so we are dealing with exponential functions, and that's gonna come back into play here and just in a couple of examples. Geometric means. We talked about arithmetic means yesterday. We said when you have two non-consecutive terms, the terms in between them, the missing terms, those are called the means. So if it's a geometric sequence, they're geometric means. So here we're asked to write a sequence with two geometric means between 480 and negative 7.5. So I mean, I'm starting with 480, I'm ending with negative 7.5, and there's two blanks in between. They want us to fill in those blanks. We did this with arithmetic means in part 2, and to be able to do this, to continue the pattern with arithmetic, we had to find the common difference so we could figure out what are we supposed to add again and again to get there. But this is geometric, so we're looking for what are we supposed to multiply to get from here to here to here, right? We're looking for our R. We have to find our common ratio first. Now what's given is the first term is 480. And the last term is negative 7.5. Now, what term number is the last term? Like this was term 1. This is term 4. Okay, so we can use this information to work our equation backward to find out what that R is and get this filled in. Okay, so we know that A sub n is negative 7.5. We know that the first term is 480. And we know that the term number n was 4 to get that negative 7.5. So we're going to work this backward to find R. So this is negative 7.5 equals 480 times R to the 4 minus 1. So same thing we did on the last problem, kind of like this, where we divide out the coefficient. So we're going to divide out 480. Okay, so the 480 is gone. Over here, that reduces, excuse me, that is 1 over 64, negative, excuse me. And I'm left here with R cubed. The 4 minus 3, or 4 minus 1 is a 3. So how do I get rid of the cube? Take the cube root. Okay, the index should match the exponent there to get rid of it. All right, so over here, the cube root, you can take odd roots of negatives. I had some people saying, I thought we couldn't do this to negatives. You can't take the even root of a negative, you get imaginary numbers, but you can take the odd root. So the cube root of -1 is -1, and the cube root of 64 is 4. So there's your R value. So now I know what I'm multiplying by up here. I'm multiplying by -1/4. Or how else could I think of that? Instead of multiplying by -1/4, I could think of that as dividing by what? I'm changing it from multiply to divide, so I flip it, right? It's dividing by -4. Okay.
Couldn't you, like, instead of reducing the fraction, couldn't you put -7.5? That, or does it have to be reduced?
No, you could have left it as a decimal, and your final answer here would have been 0.25 instead of 1/4. You just would have had a decimal.
Okay.
That's okay. All right, so I'm dividing by -4. I think that's easier than multiplying by 1/4. I think it's easier to think of it as dividing by a whole number or a integer. So that comes out 480 divided by 4 is 120. but that should be negative because it's a positive divided by negative. Now negative 120 divided by negative 4 is positive 30. And then 30 divided by negative 4 is negative 7.5. So remember those mean questions, the arithmetic mean or the geometric means? Like it checks itself at the end. If you take it that one more step, you can see, yeah, that's what I end up with. It checks out. Does that make sense? All right, now, series. Remember, a series is just the sum of all the terms in a sequence. So we said an arithmetic series was the sum of all the terms in an arithmetic sequence. So a geometric series is the sum of all the terms in a geometric sequence. Okay, that doesn't change. Now, there are different types of sequences and series. There are finite and there are infinite. Okay, so here we are looking at finite geometric sequences. What does finite mean? Yeah, it does not go on forever. It ends. There's a set number of terms. So if that's the case, you can find the sum of all the terms if you know the first term, the common ratio, and the number of terms. Okay, and plugging into this formula. If you don't know in the number of terms, but you do know a sub in here, that's the last term, you can use this formula. So there's two formulas you can use depending if you know the number of terms versus the last term. Okay, and both of those will work. The sigma notation is similar to what we talked about in part 1 and part 2. Sigma means we're doing the sum. You have your lower bound and your upper bound. And then the model over here for the sequence is the exponential expression. It's the first term times the ratio to the power of I minus 1. And they are using I for their lower bound number for their variable because they used n as the upper bound. But it really doesn't matter what variables you use. All right, so we're going to try that. We're using these equations and recognizing sigma notation. So for example number 7, we're in sigma notation. I know the number of terms. How many terms am I adding here? What's this asking? Okay, so the sum of terms 1 through 12, right? That's what they're asking for? Y'all agree?
Yeah.
Okay, so if I know the number of terms, then the formula is the first one, which is the first term times 1 minus r to the power of n over 1 minus r. So now I just need to figure out what to plug in where. Well, the number of terms, how many terms from 1 to 12? 12 terms. And we can see that was that n right there, right? What is the first term of the sequence? This sequence. How did you know it was 4? Yeah, it's the first term is that coefficient in front of r. The number being raised to the power, that's r. The number being multiplied by that, that's the first term. You could also, if you forget that, if I actually plug in a 1 to get the first term, 1 minus 1 is 0. Anything to the 0 power is 1. 1 times 4 is indeed 4. So 4 is the first term. Okay, and then we need the common ratio. What would the common ratio be here? The 0.3, very good. That's what is being raised to the power there. You have the first term times the ratio to the power. Okay, so we've identified the parts that we need for our formula. So this is 4 times 1 minus 0.3 to the 12th power over 1 minus 0.3. You can do this all at once in the calculator. You could do the numerator and the denominator separately, then divide, then multiply by 4. However you prefer to type that in the calculator. This comes out, I'm rounding here, so approximately 5.714. I'll get you a picture real fast of how I typed that in the calculator. Right there. Copy that. Of course, it's going to take it to the top. Let me bring it down. Okay, so there it is. That's how I plugged it into the calculator. So far, so good? All right, let me just get those highlighting done. Make sure we have that for the notes. Okay, now 8 is a little different. They don't give it to you in sigma notation, and you don't know the number of terms. Here, we knew it was 12 terms because of the sigma notation said terms 1 through 12. Here, it just says, find the sum of the first n terms, and I don't know how many terms there are. If I don't know how many terms there are, let's look back at the formulas. I have to use the second formula, right? That I don't need n for. So this is the formula I'm going to have to use on this one. So it is a sub 1 minus a sub n times r over 1 minus r. So this is the formula I have to use here. Now, I do know the first term. They gave that to me. What is it? It's -8. Okay, I do know the common ratio. It's -4. And then a sub n, they tell that to me. Remember, that is the last term. So I don't know how many terms it takes to get there, but the last term is 131,072. But that's all I need to be able to answer this question. So I would have -8 minus 131,072 times -4 over 1 minus -4. You can break this down. You can do the numerator and denominator separately, then divide, whatever you prefer. But that comes out to be 104,859.2. All right. Feel okay about that one? Now, those were both examples of finite sums, okay? Finite series, because there was a set number of terms. Now we're going to look at what about when it is an infinite sequence or series. Okay, so you need to remember what we talked about in part 1 of our notes. We said we could find the sum of an infinite series if it converges to 0, meaning if the end behavior, if it approaches 0, right? That's why the linear functions, arithmetic series were linear, like this. Those were divergent. They did not converge on 0. Those were divergent because they were linear. So they didn't converge on 0. They had no limit. So we could not find the sum of the infinite arithmetic series. But geometric series are exponential. Okay, so here's a little quick visual refresher of exponential functions. If you have an exponential function that is increasing, your curve is going up to the left. It is increasing left to right. This function right here is divergent. It has no limit. So you cannot have a sum. And not is misspelled in OT, not in TO. Okay, this series right here, this picture on the left, does not have a sum of an infinite series, geometric series. However, on the right, if the sequence is decreasing like this graph is definitely converging to 0. Okay, it's like it's approaching an asymptote at 0. So this one, we can find the sum. Okay, so this is the one where you would use this formula right here. Okay, you would take the first term divided by 1 minus r. And again, this is only if r is less than 1. That's how we determine which of these shape, because we're not going to graph every problem. Okay, we just look at the r value and we ask ourselves, is r greater than or equal to 1? If so, it's divergent. It will not have a sum. If it's less than 1, though, this is a decreasing function, which means we can use the formula and get the sum. And the only thing different in the sigma notation is that your upper limit is now infinity. So we know it's infinite. So far, so good. Does that make sense? All right. So in this example 9, we start out part A with sigma notation. We know that it's infinite because the upper limit is infinity. So we want to know if we can find this infinite sum. Now, before I go and start plugging this into the equation to try and answer it, I'm going to first ask myself, what is r? Is r greater than 1 or less than 1? So what part of this is r? The 0.6. Okay, so r is 0.6. And the test to know if there's going to be a sum or not is the absolute value of r is greater than or less than 1. So what's the case here? Is it greater than or less than? Less than 1. So this one checks out. Yes, it's less than. We are going to be able to get the sum. Okay, if this r is less than 1, you will be able to find the sum using the formula. And that's not an A, I'm an S. Okay, so the sum would be the first term over 1 minus r. So we've got r. What's the first term? So this would be 4 over 1 minus 0.6, which is 0.4. So 4 over 4/10, that can flip and multiply, that's 10. Okay, so the sum of that infinite series is 10. Now in B, they don't tell us the sigma notation or the equation. They just give us the first 4 terms in the sequence. So to identify R, we have to figure out the pattern. And we do that by dividing, right? So we would say we could do 0.3 divided by 3, like that. Or we could do 0.03 divided by 0.3. Okay, or any of those. When we do that, they all come out the same. That is 0.1. So that's R. R is 0.1. So we ask ourselves, can we even get a sum here?
Yes.
Yes, because 0.1 is again less than 1. So yes, we are going to be able to find a sum here because this is less than 1. So we use that same formula. We do the first term over 1 minus R. What is our first term here? 3. It's the first term listed in the sequence, and we said R is 0.1. And that reduces and comes out to be 10/3. Do some highlighting here. So we found R, got that plugged in. Our first term was 3. That came from right here. All right, last but not least on this one, part C. Oops, too far. Okay, I need to figure out the R value here. So I'm going to do 0.66 divided by 0.33. That's a 2. So if R is 2, is the absolute value of 2 greater than or less than 1?
Greater than.
It is greater than, which means what? We can't do it. We don't even need to bother plugging into the equation because this will not have a sum. And notice the numbers are getting bigger, aren't they? They're doubling, they're getting higher, higher, higher. So that is divergent. It's going up to infinity. It's no limit to this sequence. So we could tell that way or using this rule. But because I'm going to write it out for our notes, because R is greater than 1, the sum does not exist. Y'all okay with that? So you're checking your R, is it greater than or less than 1 to determine if your infinite series can have a sum. All right, and we're going to knock out this last one. It'll only take like 2 minutes. We've got time. We are told we are buying a house and we want to write an equation for the value of the house. The initial purchase price. Let me write this equation out in minus K here. Okay, the initial purchase price is $225,000. Okay, so that's what we're going to have as our A sub K. And then they tell us that the home appreciates 3% each year. What does that mean? It goes up in value 3%. So the value of the house is not going to be 0.03 though each year, right? It's going to be what you originally paid plus 3%. So won't that be 1.03? That's 103%. Does that make sense? It's the original 100% price that you paid plus the 3% it's appreciating. So that's R. And then K, this initial value we used, this was not, because N is representing years, this was not year 1, this was year 0. This was the initial price, right? So this is actually A sub 0, that's 225,000. So K is 0. So that's what we're going to plug in for K. So the equation is 225,000 times 1.03 to the power of N. This is what we could use to find the value of the house after N years. Okay, y'all have a good one. I'm gonna go ahead and finish this video since I'm recording. I'll go over B with y'all in class tomorrow. All right, so those of you watching the video, if this is the equation we came up with, and then this part says, well, how much is it worth after 10 years? They're just saying plug in a 10 for n. So we're using the equation we just came up with and plugging in a 10. Okay, so we input this into the calculator, and after 10 years, that would come out to be $302,381.19. And that's it for those notes. So there's a Delta Math activated already. You'll have the full day of class tomorrow to work on it, but if you want to start it, you can.